Hello YouTube, we're back. Alright, so today's what, day 6? We're doing ordinary first order differential equations in uniformly accelerated motion without friction. Then we'll talk about friction. So, realize what we've done. The last couple of weeks, packets 101 and 102 were sort of a gentle introduction to Calc 3, Vector Calculus, calculus in 3 dimensions, right? Now I'm going to give you, this week, a little gentle introduction to Calc 4, advanced topics from Calc 2, like differential equations. Alrighty, so let's do it. Consider the baseball problem. And pretend that a major cataclysm is befallen the Earth, so that there is no atmosphere, so there's no friction. Alrighty. That's a big setup. Okay. You're at bat, you hit the ball, and calculate its trajectory before it hits the ground to see if you hit a home run. Baseball stars do calculus while they're playing baseball? Do they?
Jeter did.
Alright. You can accomplish this easily if you decompose the trajectory into horizontal and vertical components. Uh-oh, vectors again. Assume that the horizontal component complies with constraints of uniform motion and that the vertical component complies with constraints of uniformly accelerated motion. What? Well, horizontally, let's say it has like an initial velocity or something. When you hit the ball, right? There's a horizontal and a vertical component to the velocity vector, right? So horizontally, let's say there's some initial velocity, and that's it. It's just going to stay the same. Horizontally, you have a constant velocity, but vertically, you don't. Why? Acceleration due to gravity. Okay, so there's your accelerated, uniformly accelerated motion model. Okay. At t equals 0, you hit the ball when it's 3 feet off the ground. The velocity of the ball at the time of impact is 207 feet per second at 40 degrees. What? The vector at t equals 0 is 207 feet per second at an angle of 42 degrees. So this is a velocity vector, but it's given you in polar form. It's given in polar form. So it has a magnitude, 207, and it has a direction, 42 degrees off the horizontal. Okay? Alrighty. And g is negative 32 feet per second. Alright, so can you write the acceleration vector at 0?
Yes.
What is it?
0.
0.
Negative 32.
Negative 32 per second, right?
Okay.
Alright, so no acceleration in the horizontal component, but acceleration in the vertical. Alright, how about the horizontal and vertical components of V0? Now we have V0 in polar form. I want it in Cartesian form. What's the horizontal component? Remember how you get the horizontal component of a vector? Cosine. Times the cosine. Okay, so I'm going to write 207 feet per second, right? Cosine of 42 degrees for the horizontal component and the vertical component. 207 sine, right? Just like when we did polar coordinates, r cosine, r sine. Remember that? The very first week at school. We did that stuff. And this is feet per second. Fun. And what's your initial position? I'll call that r of 0. Where are you horizontally, let's say? Let's make it easy. 0, but vertically? 3, right? Because we're hitting the ball 3 feet off the ground, right? When you hit the ball with the bat, let's say at that moment it's 3 feet off the ground. Alright, that's part A. Good. Alright, part B. Write A of t, V of t, and R of t. Alright, so these are like initial conditions. At t equals 0 for the acceleration, for the velocity, for the displacement. Can you use that to figure out A of t, the acceleration for all time, V of t, the velocity for all time, and R of t, the position for all time? Well, let's see. What do you say? Is the acceleration going to change?
Oh, crap. I started using G.
Start using G? Well, actually, you're ahead of me. If you did that during question... I don't have to have it. Yeah, but also, you don't have my question. Right.
I used it for B, C, and D.
Yeah, I think if you did that, you're looking at question 3 already.
Yeah, no.
Alright. Alright, so the acceleration is not changing, so leave it. Uniformly accelerated motion. The acceleration is a constant. It could even be 0 instead. You see right there. Alright, what about V of t? What did we say about the horizontal component?
constant.
Here's V of 0.
158.
158.
0.83.
Oh, you actually worked this out?
Yeah.
I'm going to leave it in exact form, but yeah, you can do that. But the thing is that it changed. The horizontal component is not changing, right? Because the acceleration in the horizontal direction is 0, so it's not going to change. What's changing is the vertical component. So I'm going to keep this at 207 cosine 42 degrees in degree mode. What about the vertical component? What do you say? Since the VDT in the vertical component is negative 32, how to get V in the vertical component? Variable separable. This is the beginnings of Calc 4, reviewing variable separable and then going crazy with differential equations. Okay. So what do you do? dV is negative 32 dt. So if you anti-differentiate, you get V is negative 32t plus some constant, right? Now, where's the constant coming from? The initial condition we have over here. That the vertical component of V0 is 207 sine 42. Okay. At t equals 0. All right, so I'm going to put in 207 sine of 42 when t is 0. So guess what c is? So c is? No. This is 0. What's c?
207
Sine
sine 42.
207 sine 42. So I'm going to write it this way. Negative 32t plus c, which is 207 sine 42. All right, so you solved your first difficult. Wow. And how about r of t? What about r of t? Well, same idea. You're going to anti-differentiate this, right?
What does R stand for?
R is in position. Horizontal vertical position. Right? So R of t, I call it R of t instead of S of t, like displacement, because it's like a radial vector from the origin. Right? All right, so what are you going to do for R of t?
Speed times time.
Well, this is dx dt up here, right? Right. So dx dt is 207 cosine of 42. Well, I'm breaking it up into horizontal and vertical, so it's x and y components, right? So 207 cosine of 42 degrees. What do you do to get x? All right, so dx is 207 cosine 42 degrees dt. So integrate and you get what? X equals what? 207 cosine 42 degrees t plus another constant. But what's the initial condition for x?
3. Oh, wait, 0.
X of 0 is 0, right? So, what's c?
0.
0. Okay. So we're gonna get, okay, I'm gonna put 0 here, dang it. Put 0 here and 0 here, so c is clearly 0. So I can write here that R of t is simply 207 cosine 42t plus 0. Alrighty. How about your vertical component for R of t? You're going to have to differentiate this, right? Down here?
Yep.
Okay, so if y of t is that, dy dt is that, plus 207 cosine. Alright, so how do you solve that difficult? Very basic difficult today. Is it sine? Oh, I thought it was right. We did the cosine part. Yeah, I'm keeping this in exact form so I don't have any round-off error for later when it asks you some questions about like what's the maximum height, what's the maximum range, and so forth. So dy is negative 32t plus 207 sine of 42 degrees dt. So, and to differentiate that, and you get y equals negative 32t squared over 2 is negative 16t squared, right? But then plus 207 sine 42 degrees. This is a constant. It's just a number. What if it said 2 dt? You integrate and you get 2t. So stuff t plus a constant. Now how do you get that constant? Look at the initial conditions for the vertical component of r. R0 starts at 3, the vertical component. So if you plug in 3 for y and 0 for t, trying to make it easy here, guys. C's got to be 3. Okay, so C is 3, so there's your answer. Negative 16t squared plus 207 sine 42t plus 3 is what goes here. Alright, so that's the answers to A and B. Alright, so but this, we've done this kind of stuff before. This is not new. We're going to get into crazy stuff. Alright, so part C. What's the maximum height of the ball and when does it reach this zenith? So what do you do to figure out the maximum height? Set the velocity equal to 0, but which component? Let's see, you know the velocity here? The y component. We're going to set that equal to 0. Solve for t, and then plug it into this and figure out the maximum height and where it occurs in the x component, I guess, if you want, right? All right, and I guess this is where how comes into play. All right, so we're going to set the vertical component, negative 32t plus 207 sine 42 of the velocity equal to 0. And so how do you get t? We'll subtract. Okay, so negative 32t equals negative 207 sine 42. Yeah, now what? Alright, so t is positive 207 over 32 sine of 42 degrees. And if you want to see what the heck that is, it's time for Hal must die. So Hal, where are you? Alright, let's work that out. What is it? It is 207 divided by 32 times divided by 32 times the sine of 42 degrees. All right, so here's second sine. I know, 42. Now let's check our mode. I guess we're in physics class, so we're going to be in degree mode for a while. So I'm going to switch it. Well, give me a test. 0.4328 seconds. 4.328. I didn't say that? That's it? Okay. So, 4.328 seconds. Now this is an approximation just to see how big it is, but we're going to use its exact value to plug into R. Okay? So plug into R.
What is this one?
What does it say?
What is this for? Entire.
This is part C on the packet. 1C on the first page. Well, I don't know if that's my first page. Might be your second first page. Okay. So that's when it attains the maximum height. So how do you figure out the maximum height? Plug it into the y component, right? Alrighty. So here's the y component. I'm going to plug that value into here. And, well, by the way, let's figure out what this is just to see. No, not into here. Sorry, the R. Where is it? Where's this calendar? Alright, so you're going to plug that value into t here, t squared into the t here, and the t here. It asks for the maximum height, but I'm curious where it occurs horizontally too. Alrighty, so, God bless. So let's do that. So let's see, what am I going to say? I'm going to call this, let me give this a name. I'm going to call this TZ, for zenith. So what I want to do is figure out the vertical component of R at TZ. And the horizontal, just out of curiosity, didn't ask for it, but at that time also. Let's see what that is. All right, and now we can do it in HAL too. So where's HAL? All right, HAL, baby. Last time we see HAL. You see your desktops? Yeah. HAL's going away. Realize that the Inspire is basically HAL with a different interface. That's all it is. It does all the same stuff that HAL does, right? Sure. It's a different interface. It's in color. It's easy on the eye. It's higher resolution. Has a document system to save your work, but it's basically HAL. All right, so let's do this. I'm going to do -16. Wait, how about if we store that somewhere? I'm going to store that answer. Store it as T. So now I want -16 T squared. What? Oh yeah, there's a throttle. Yeah, that's ludicrous speed. Throttle. If you throttle it, it's ludicrous speed. All right. Plus 207 sine of 42 T. Now notice we already substituted in for T, right? Plus 3. And there you go. Now, since T was already in decimal form, it's giving you the answer in decimal form. And it rounded it off for you to 3 places nicely. Okay, that's nice. So what should I write for this? What should I write right here? 302.766 feet. All right, so that's the maximum height of the baseboard, right? So it starts at 3 feet, it goes up to 302 feet. Where does that happen? In the X component. Plug it in. Right. So again, the X component, what was the X component? Of the position was 207 cosine 42 times T. So bring back HAL. Let's do that. All right, I already have T stored there, so I'm just going to do 207 cosine of 42 times that T. The T's already been plugged in, and it's 665.842 feet. Just, it didn't ask for that, but just for curiosity's sake, there it is. 665.848, right? Right, so I was trying not to round off before, right, in terms of sine 42, in terms of cosine 42, so that I can round off here. And not have to round off there. All right, so that's 1C. Any questions on that? This is not new. We've done this. All right, 1D. Find the range of the baseball, in other words, when it hits the ground. So what are you going to do? Right, the vertical component of the displacement is 0, that's when it hits the ground. Right, so you're going to set this equal to 0, solve for T, and then plug that into your R to figure out your horizontal range, how far horizontally it went. Okay, so let us do that. So this is, yeah. Okay, we'll talk about that. All right, so this is the vertical component, right? Okay. So let's set the vertical component, which is -16T squared plus 207 sine 42 degrees T plus 3. Let's set that equal to 0. And, well, how are you going to solve that equation? F2 solved? Okay, 2 for a day? How about do it graphically? Let's do some graph. That's perfect. Alrighty, so how about y equals, I'm in, what am I, function mode? Clear that. Alright, let's just put this in. Now I'm in function mode, so the t's are going to be x. -16 x squared plus 207 sine of 42. Again, I'm x for function mode. Where's the 42? Plus 3. Okay. Now let's graph that. Any idea what a window for this would be? I'll just do this in 4. Is that a good window? No. If you plug in 0 for t, what should you get? Well, wait a minute, what happened? Did I answer that right? Yeah. Should it go through 3? Where's my trace? Huh? First one's not tracing at 0. Alright, second window, X res 1. Regraph. Okay, so trace. It should go through. There we go. Why didn't it say that? Okay, so it goes through 3, and then, well, how far does it go? I want a complete window here so I can get the 0, right? So what are you going to do? How big do you think this gets? This is the y component, right? Remember the y component went all the way up to what? 300 something? The question is though, how long does it take?
8.67.
Well, remember it took 4 point something seconds to get to the zenith. So you're going to take at least that much to get to the ground again, right? So how about if I change the window? Remember, if this is x min, x max is really t. How about 0 to, I don't know, 10? And how about the y min and y max? How about 0 to, I don't know, 400? Because we know it goes up to 300 something, right? What was it, 300? Huh? 302, right? Okay, so there you go. So how about 100 here? And let's get a complete window. There you go. So now remember, this is not a trajectory, this is just y graphed versus t, the y component of displacement. And I want to know when the y component is 0. Now, yeah, there are 2 roots, but one of them is negative. What's this, Back to the Future? You got a time machine or something? Before you hit, when you hit the ball, t equals 0. So t is negative is before you hit the ball. That's not part of the problem. I mean, if we go backward in time, I guess it hits the ground. I don't care about the negative root. I want this one over here. So how do you get it? Remember, showing off HAL stuff. You know HAL stuff. What do you do? F5, 0. All right, so lower bound is before the root. Let's get closer to it. The wrong one. Yeah, I'm like, oh, really? It does that? Yes. All right. Enter. Okay, now y is positive, enter. Now I want to go where y is negative. Enter. And by the intermediate value theorem of continuous functions, there must be 0 between somewhere, and it's at 8.678-ish. Okay. So what if I call that TR for the time it takes to hit the maximum horizontal range? And TR graphically came out to be 8.678 seconds. All right, now what do you do with that? Plug it into who? R sub x, right? Okay, now R sub x, is it still here somewhere? R sub x, I had it to that. The horizontal component for the displacement is this thing, 207 cosine 42 times t, right? Okay, so let's take our t value, that, and use HAL and plug it in. Okay, so that's going to be 207. Let's see, where is that answer? I'm going to plug that answer in.
Mr. Garcia, if the ball started 3 feet above the ground and it took half that time to get to the top, wouldn't that time just be to get 3 feet off the ground again? Wouldn't it still be going?
Well, I'm not doubling the time. That, yeah, from 3 feet to 300 feet is, what was it, 4.3?
It's like 4.3, yeah.
4
It was half of that.
But it's not half of that.
It's not.
Right, the axis of symmetry of the parabola that we just drew includes that negative 0 and the positive 0. So half the time from the negative 0 to the zenith, that's half the time, double that, from that negative point. It's not symmetric with respect to 0. It's symmetric with respect to the other root, right? All right, so let's do, so we're basically doing this with a sine, right? No, it is cosine. Wait. Okay. We're doing this, but with a different time. Okay, so how am I going to plug in that time? Where is that time stored? No? All right, do this. Isn't that x alpha c? There it is, right? The x coordinate of that point of intersect we just figured out on the graph. So I'm going to do this, but I'm going to put xc here, x alpha c. And I get 1335.02, well, it's running off to 3 places, to 2 places. I have a little bit more here. R sub x at t sub r is about 1335 at 0.019 feet if we actually get a fixed 3. I guess it's on float somewhere. Alrighty, so did we kill off 1a, 1b, 1c, 1d? That's 1d. Alright. Then 1e. Eliminate the parameter t and find the trajectory as y is a function of x. Graph the trajectory using function mode, showing that it is parabolic, and label the x and y coordinates when you hit the ball, when the ball reaches the zenith, and when the ball hits the ground. And if this is Fenway Park, can the ball go over the outfield wall? All right, well, I'm going to cut to the chase. To eliminate the parameter t, what's involved? Do you have to Pythagoras? Right, instead of x is a function of t and y is a function of t for your displacement, I want y is a function of x. So if x equals this first part, and we solve for t, and then so t would be x over 207 cosine 42, plug that into this t, and then you got y is a function of x, and you can graph that in function mode, right? Or you can graph this in parametric mode. You should see the same thing. Remember parametric mode? But I want to save a little time here. I'm just going to graph what I got. Don't I know what's going on already? I can graph this without a half. I know that this is the zenith, 302, 665. I know it starts at 0, 3, right? And I know it goes over to 1335. Okay, so just graph that. The point being here, if we don't keep track of friction due to air resistance, the trajectory is parabolic, right? If you graph it using the f of x, you're going to see that. The point is that if you throw in friction, if there's air resistance vertically and horizontally, the trajectory is not parabolic. Do you know what it is? You know what it looks like? What a ballistic trajectory looks like, in other words, with friction? It looks parabolic and then it just drops down, right? So because there's not only resistance due, it's sort of like resistance due to gravity pulling you down, but there's resistance pulling you up, right? So the y values are decreasing at a lesser rate, but the x values are now decreasing because if the x velocity is not constant anymore, it's being slowed down by the air resistance also. So instead of doing like this, since the x component is slower now, it's going to do like this. And that's what the next packet is. So I want to get to the next packet. So let's just graph what we got. All right, what do we got? We got. So let's see. It goes over to 1300, right? Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, it goes up to 1335 something. Let's say that's here. Count to 0. It starts at 0, 3. Now it goes up to 400, almost 400, right? So 1, 2, 3, 400. It goes up to 300, what's it? 30. Oh, here it is, 302-ish and 665-ish, right? So 1, 2, 302-ish. No, 1, 2, 3, that's the x component, 6. 1, 2, 3, 4, 5, 6, 7, so 665-ish and 302-ish, so around here. And it starts at 0, 3. If this is 100, 0, 3 is going to look like 0. So it's going to look sort of like this. Okay, so it's like a trajectory in this direction. So it's more or less parabolic, all right? So there's your x component, there's your y component, there's your origin, and there you go. I guess we could label some points. This is the point 0, 3. This is the .665.848, comma 302.766, and this is the point 1335.019, comma 0. All right. Now the thing is, do you know how big the green monster is? They're talking about Fenway Park. You know how big? Who's it to baseball? Not I said right now. Huh? No? All right. The green monster is like a huge wall, apparently. What? 312? I have 310 feet. But okay. That's how far out it is, right? And then it's 37 feet tall. So at 310, was it 310? 310-ish, almost 311. 1, 2, 3, 11-ish. You're talking about a wall that's 37 feet tall. Say that, that's even more. If that's 100. Say that's he killed it.
It looks like that big on this graph.
Here's the wall. It's not even as big as a tapeworm. There's the wall. So did you hit a home run? Yeah, because these numbers are way too big. There's something wrong with these numbers. All right. Yeah, no one's gonna hit a home run that humongous, but whatever. Yeah. Yeah, that was 1E. You can't always do this, but sometimes you can eliminate the parameter t from parametric mode and go back into function mode. So if you solve, since this is x equals this, right? X equals 207 cosine 42t. Could you solve for t? Right? Just divide by 207 cosine 42. Right? Is that okay? You don't look too convinced. No. Yeah. So t is x over 207 cosine 42. Plug that t into here, and you're going to have x's. Y is a function of x. That's all it is. So if you graph that, you would see the same thing. All right. So there you go. Now, for homework, you can try number 2, which is the same problem on the moon. What's the only difference? Again, no air friction, right? But different constant in gravity. So it's going to go a little higher, a little farther, probably. Let's see what you get. That's all. Okay. Now, let's take a look at friction. How do you model friction?
Ding, time to go.
All righty. So here's the next package. So this is where it starts getting crazy. Today was just warm up, refreshing, that you know how to do difficult. This is on the Dropbox anyway, in case you lose it or anything.
So homework's number 2 in the other package. This is just
Right. This we're going to do this basically tomorrow. But the homework tonight is the same package we were just doing, number 2. We did number 1, right? So do number 2 the same way. You're just on the moon. Now this problem is the same idea, except we have to model friction due to air resistance. Okay. All right. So for the benefit of the YouTubers, we're here. All right, so now we're going to talk about exponential decay and approach models for friction and non-uniformly accelerated motion. The acceleration is not a constant. So we're modeling free fall with friction, in other words, a real ballistic model. Reconsider the baseball problem and forget about the major cataclysm. You must have had a nightmare. Maybe it was that burrito you had at Taco Bell. Oh, that was funny. Okay, now the question here is, the problem here is, how do you model the friction? Okay, we still have the same A sub 0. We still have the same V sub 0. We have still the same R sub 0, but we have a different differential model for the acceleration. Okay, we're going to model it as the acceleration is directly proportional to the velocity. So the faster you go, the more air resistance there is. Does that make any sense? Yeah. Now that's not the only way to model air resistance, but that's one way we're going to take a look at that. All right, so these initial conditions and differential equations are supposed to model the first home run ever hit at Dodger Stadium. You will test this model and see if it predicts Willie Stargell's home run in 1969. So remember what A of t is, and remember what you're calculating, the velocity vector and the position vector. So here we go. Number 1. Use DE solve to find the general solution of x for x prime. Apply the given initial conditions to find a particular solution. All right. So, what the heck is DE solve? Have you ever heard of that? There's some methods or functions that we have in the TI-89 calculator that we never use because because you should be able to do this by hand. All right. So this is what we're saying. Yeah. We're about out of time, right? All right. So we'll start this tomorrow. All right, we'll start that tomorrow. So if you need a homework check-in, make sure you're doing number 2 from the 103 packet. Don't do the 104 packet yet. So we're going to focus on Calc 4 related material this week to give you a little taste of that. Advanced differential equations. We're not advanced yet, but we will be. All right, so YouTube, that was fun. We'll do 104 tomorrow. Have a nice